Hello, hello, hello. This is Nicholas on this lovely Wednesday afternoon, wanting to talk to you today about what exactly is a derivative. And this is kind of a sequel to my video on what exactly is a matrix. Now, remember that in my matrix video, the whole idea that I wanted to get across to you was thinking about a matrix as representing a linear transformation, where the columns of that matrix were the images of the standard basis vectors upon applying that transformation. Now, I want to kind of show you through this video that derivatives really aren't all that much different from matrices, fundamentally. Now, typically, we think of a derivative as, we imagine a graph, we take a point on the graph, we draw a tangent line going through that point, and we say, okay, yeah, the derivative at that point is the slope of that tangent line. And this is not really the best interpretation of what a derivative actually is, right? There's a number of assumptions that are going on in this drawing. For one, we've assumed that, let's call this function f. We've assumed that f is a real valued function, meaning that its output is a real number. In other words, its output space is R1. And we've also assumed, since I've drawn it with only two axes, that its input space is only R1, right? So this is the simplest of cases where you can view the derivative as a slope of a tangent line. Now, you can view a derivative, it gets a little bit more complicated, but for any real valued function, in other words, you have f that has, say, an n-dimensional input space, in other words, n independent variables, giving out a real number, so it's a real valued function. It outputs just a single number. You can view the derivative in this particular case still as the slope of a tangent line, but it's not really fundamentally what it's about. You can view like if you're dealing in this case and you're fixed on tangent lines, you can take view the derivative at that point as the slope of the line tangent through the cross-sectional curve on that axis, right? So if you've got f of x, y equals z, you have a graph, and you want to talk about, in this case, it would be the partial of f with respect to x, then that would be the slope of the curve, of the cross-sectional curve taken perpendicular to the x-axis. It would be the slope of the line tangent to that point on the cross-sectional curve perpendicular to the x-axis. And now you can see how that can be a little bit cumbersome to think about. So fundamentally, though, the derivative is not really about tangent lines. So let's talk about directional derivatives. So this does kind of assume some multivariable calculus background. I do have a video on the directional derivative if you'd like to watch it. In essence, though, we're faced with the question of, well, if we have a function f that has an n-dimensional input space and, say, an m-dimensional output space, right, how do we measure change? Okay, because if you imagine, try to imagine what a function like that would look like, right? It would output not a number, not a scalar, not a point. It would output a vector, right? An MD vector. And so we have actually, if we pick a point, that's not really enough, right? Because if we imagine a point on the graph of this function f, well, there's infinitely many directions in which we can measure change from. And so we need to specify both a point and a vector in which we're measuring the change. Say from the point 1, 2 in the direction of 1, 3 or something. Maybe that's that vector on that point. I'm not really sure. But you need to specify both in this case. And so the directional derivative is best thought of, in this case, as a scaling factor between this higher dimensional function f. So if we think of f as being parameterized with respect to t, then what we say is that df over dt is equal to this is how we write it, the directional derivative at the vector v, so in other words, that's the direction of the change in which we're considering. That would be this vector here, v, of the function at the point A. So this would be the point A right here. It's going to be that times the magnitude of the change in the input, assuming that x changes only in v's direction. So what this means now, if I'm breaking this down, is that we have a change in the input, a tiny nudge in the input, and it produces a corresponding change in the output. The directional derivative then is just the factor that relates the two. So the directional derivative tells you how much your output changes given an input change. So that's one way to interpret it, or it can approximate the change in the output given a discrete change in the input. And so now the directional derivative really is very interesting because, well, on the one hand, we define the directional derivative, d sub v of f of a, to be the derivative with respect to t at time 0 of f of a plus tv. Now, what this means is that we are in essence doing this like kind of brute force calculation. So instead of viewing a as being a fixed point, we view a as a vector, and we parameterize this line. In essence, we have an anchor point plus a directional vector, and so that creates a line. And so it's moving with some velocity, right? V, that's why we call it V. It's moving, A is moving, our initial point A is moving with some velocity V, and at a particular time t, it's, somewhere on this line. And so we want to say, well, where is that point at time 0? In other words, at A. Kind of like how in single variable calculus, where you took the limit as h approaches 0 of, f of x plus h minus f of x, all that, all over h. So this is how we define the directional derivative. And now I want to show that the directional derivative is actually a linear transformation. So I'm going to show this first for polynomials because generalizing it requires some math that is way beyond my understanding currently. So let's consider the directional derivative for any arbitrary like polynomial multivariable function. So the way we write this is that, let's say we have a function p of x, and it's a vector x because it has n inputs. So we write this as it's going to be a sum of polynomials, so it's going to be a sum, and let's say this polynomial is going to be of degree k. It's going to be a sum such that the individual degrees of the polynomials is no less than the total degree k. And we're going to have some coefficients, c sub k1 to kn of x sub 1 to some degree k sub 1, x sub n to some degree k sub n. This notation is just kind of cumbersome, but basically it's saying that we've got a sum of polynomials. They each have some degree. That degree can be no more than the total degree k. And so now we can talk about then parameterizing the vector input x as a plus t v, right? So in other words, parameterizing our vector in terms of that line. And so computing p of x of, right, in other words, computing p of x of t, because this is really a function of t, because a and v are constants. Computing p of x of t would be absolutely massive. But what we can do is note that everything, we're just going to have the same sort of setup. In other words, everything that has a coefficient up front times some x to some power is just going to have, whatever coefficient that might be, it's still going to just be some coefficient. So in other words, what we can write is that p of x of t, or p of a plus tv, is still just going to be, say, b naught plus b1t plus b2t squared dot 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 plus b sub k t to the k. And so now what the values of these various b coefficients are, I really have no clue, but that's not really necessary. Because really what we need to just look at is b sub 1. That's really the only one that that's gonna actually be important. Because if I take the derivative of f of a plus tv and I evaluate it at t equals 0, then realize, well, this is going to go away because the derivative of a constant is 0. And then this is still going to have a factor of t, and then we're going to plug in t equals 0, and it's going to go away. And likewise for every other term. And what we're going to just be left with is b sub 1. And so b sub 1 in this case represents the directional derivative. So what is b sub 1? Well, realize that because every input, in other words, when I input a plus tv into that polynomial function, it really looks like p of a sub 1 plus t v sub 1, a sub 2 plus t v sub 2, dot dot dot, a sub n plus t v sub n. Those are the components of those vectors. And since the variable t always appears paired with one of the coefficients of v, then any term in this expansion here, that has a t must also, a single factor of t, in other words, t to the 1, must also have a coefficient of v somewhere in here. And so what this tells us is that b sub 1 is really just a linear combination of the components of v. In other words, b sub 1 could be equal to d sub 1 v sub 1 plus d sub 2 v sub 2 plus dot 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 plus d sub n v sub n. Now, what the values of d are, again, isn't really very important. The fact that this can be written as a linear combination, though, is very important, because now we know that d sub v of f of a is, well, we can essentially write it as the vector d dotted with the vector v, right? This is a dot product. And so a dot product, though, vectors are matrices, right? They're n by 1 matrices. And so a dot product is really matrix multiplication, which is really a linear transformation. And so what this means is that for polynomials, d sub v of f of a is equal to t, where t is the linear transformation, t of v. In other words, there exists a linear transformation, t of v, at the vector v, that does the same thing as the directional derivative at that point for any vector v, no matter what we choose. And so what this tells you, this property, by the way, is known as directional linearity. And so what this tells us is that there is a linear transformation that does the exact same thing as the directional derivative. And that linear transformation we write as the derivative transformation. So this is kind of uncommon notation right here. Typically, we'd write that, the way at least that I've seen it is that we say that d sub v of f of a is equal to d sub f a of v. So these look similar, but they really are two very different objects, right? On the left side, we have a directional derivative that measures corresponding changes in the output space. Now on the right-hand side, though, what we have is a linear transformation of the function f at the point A of the vector v. And they're equal to these. They're equal because, in general, really, the derivative is a linear transformation. Two properties that you might recall from like single variable calculus that may cement this fact in your mind is that, say, the derivative with respect to x of c times f of x is c times the derivative with respect to x of f of x. And you glossed over that and you're like, well, obviously, yeah. And then also the derivative with respect to x of f of x plus g of x is equal to the derivative with respect to x of f of x plus derivative with respect to x of g of x. Now, these two properties might look obvious, and you were probably originally told to think of these in terms of like adding functions together and then what the corresponding slope of the tangent line would look like. But instead, really, you can think of these two properties as the properties that define a linear transformation, right? This is linearity. The derivative is a linear transformation. And in the next video, I'm going to use this fact to derive the Jacobian matrix in about 2 minutes. And so with that, we're done.